We're going to build on the previous lesson about forces by talking about an object that's on a surface, and this object has a mass, and we're going to keep the mass the same as we had earlier. Mass 1 is 4 kilograms. So the first thing you should always draw is the force of gravity on this object and the normal force. But before we do that, let's make the problem a little bit more complicated. Let's say that there is a sled that is acting on that there's a string acting on this object like a sled. So if you have a sled and you're trying to pull it, so there is a string or a rope that is pulling on this object. And let's make it at an angle theta. So this object, there is a force, an applied force, and let's make that applied force to be 20 newtons, and it's at an angle of 30 degrees. So they're going to ask you about the force of gravity, the normal force, and so the first thing you should do is you should realize that the force of gravity is not going to get impacted. So the force of gravity is still going to be mass times acceleration of gravity. So the force of gravity is still going to be calculated by simply taking 4 kilograms, which is the mass of the object, and multiplied by the acceleration of gravity. I'm using negative 10 meters per second squared as the acceleration of gravity. So this comes out to be negative 40 newtons. However, the normal force will not be negative 40 newtons. The surface doesn't push back up 40 newtons because now what's happening is this rope is interfering. The rope is doing two things. The rope is pulling towards the right, and the rope is pulling upwards. It's doing two things at the same time. We call the force that it exerts on the object toward the right as FAX. It's the X component. And this one, the force that's pulling upwards, we can call that FAY. It's the Y component of FA. How do you find FAX and how do you find FAY? Well, it's very easy. You're going to simply use cosine theta and sine theta. So cosine theta, and your theta is 30 degrees, so you can plug in 30 degrees in for your theta, is equals to adjacent over hypotenuse. Your adjacent side is FAX. Your hypotenuse side is 20 newtons. I'm going to right now just leave it as FA. You can plug in whatever numbers you want to depending on the problem you have. So to solve for FAX, you just multiply both sides by FA. So FA times cosine the angle, cosine theta, is going to give you FAX. So FAX is simply the hypotenuse, FA, times cosine theta. 20 newtons will go in for FA, and you multiply it by cosine 30 degrees. Same way, how are you going to find FAY? Well, you're going to do the same exact thing, except you're going to use sine theta. So sine theta is opposite over hypotenuse, and you're going to use the same principle. Sine theta is equals to FAY over FA. So FA times sine theta will give you your FAY. So I don't have much room here, so I'm just going to put an arrow, and I'm going to say FA sine theta is my FAY. Why is this important? Well, this is important because this box is now not pressing against the surface with a force of 40 newtons. Because what's happening is the force of gravity is pushing the box downwards 40 newtons, but the string, the rope, is pulling up with a force of FA sine theta. So what's the net force? What is the total force with which this box presses against the surface? The total force with which this box presses against the surface, the net force on the y-axis with which this box presses against the surface, is the force of gravity, which is pushing down, minus FAY, which is pulling up. So mg minus FA sine theta. This is the actual force with which the box actually presses against the surface. This force, if this force is not bigger than the force of gravity, then the box will still press against the surface, but it won't press against the surface as much as it would press against the surface if the string was not present. So this is going to be the net force that the box is pressing against the surface with. So that means if the box doesn't go through the surface, that means the surface is holding up the box. That means the surface just has to balance this force, mg minus FA sine theta. So the normal force, which is the force that the surface exerts on the object to keep it in balance, is simply going to be the same strength as mg minus FA sine theta, and it's going to be a weaker force. So the arrow is supposed to be pointing upwards. Let's give it a different color. So the normal force that the surface is exerting on the box, normal force is simply going to be mg minus Fa sine theta. This is useful because later on they may ask you to find the force of friction. And remember, the force of friction is found by taking the coefficient of friction, whether it's kinetic or static, and multiplying it with the normal force. So you have to calculate, you have to get the correct normal force to plug in here to get the force of friction. A couple other questions they may ask you. They may say, okay, what happens if this box does not move? Well, if the box does not move, you know that there must be a force of friction preventing it from moving. So if the box does not move, then the force of friction on this box, which is pointing towards the left, must be as strong as the force that's pushing it to the right. So if they ask you, what's the force of friction? You'd say, well, the force of friction is exactly as strong as Fax, or exactly as strong as Fa cosine theta. And I'm going to leave it in variable form because you can plug in 20 newtons for Fa. You can plug in 30 degrees for theta, and you can solve this. I'm just going over the concepts with you. So in this particular case, if the box does not move, the force of friction is as strong as Fax. And I want you to know how to calculate the normal force. In this particular case, the normal force will be the force of gravity, which is pushing down, minus Fay. Whatever is left is called the net force. It's called the sum of the forces on the y-axis. Force of gravity minus Fay. And thus, that's the only force that the surface has to balance. So the normal force will be mg minus Fa sine theta. These are useful ideas to know because they may ask you in this problem, find the coefficient of friction. Well, great, you just now found out the force of friction. This value is going to go in for the force of friction. This value over here is going to go in for the normal force. You divide the force of friction by the normal force, and you're going to get the coefficient of friction. So you can do a lot with these concepts as long as you understand them, and that's the important part. The other thing, before we leave, I want to tell you that if the box is not moving, then the force of friction is the same as Fax. But that also applies if the box is moving at a constant speed. Let's say something got the box to move. So to get the box moving, the Fax had to be greater than the force of friction. So let's say the box was at rest, Fax was greater than the force of friction, so the box accelerated, increased to a certain speed, and then Fax decreased because the string didn't pull as much. So whatever the case is, whatever got the box moving, once it starts moving, if it maintains a constant speed, a constant velocity, if it's not accelerating, because that's what it means when somebody says constant velocity. If the box is moving to the right at a constant speed, a constant velocity, and if they ask you then, what's the force of friction? Well, then also, the force of friction is going to be exactly as strong as Fax because there's no acceleration. If there's no acceleration, that means the force pulling to the right is being balanced by the force pulling to the left. And no acceleration could be either an object at rest or an object moving at a constant speed, because both scenarios have acceleration 0. So hopefully this was useful, and we will put up another lesson soon talking about forces, and we'll keep building on these ideas.